All right, welcome back. This is 12.2, and we're going to talk about the chemistry of buffers. And this is still continuing chapter 17 on acids and bases. All right, so most biological fluids that we have in our body are solutions whose pH must be maintained at a constant pH with a very narrow range. For example, your blood that's used to transport your oxygen depends on a pH remaining at about 7.35. And if this pH of your blood were to deviate more than a 0.1 of a unit, then it would lose its ability to perform its function carrying oxygen. So it would be not good. Many of the products of the metabolic process that are occurring in your body right now are acidic compounds. Each is able to lower your blood pH to fatal levels if you didn't have a buffer in your blood. And foods that we enjoy eating are full of acidic compounds like lemons and tomatoes and hot sauce and things like that. So if our blood didn't contain some kind of buffering solution in it, then it would definitely change our blood more than a 0.1, and that would be fatal. Okay, so we couldn't live without our blood being a buffer. So one thing about buffers is you must know that list of strong acids and strong bases. I mean, you just have to, when you hear it, recognize that it's a strong acid or a strong base. Or if it's not one of those, it's not a strong acid, which means that it's a weak acid or a weak base. Okay, so let's review some concepts here. Ka is the dissociation constant for an acid. And it's when we have an acid, HA, and A is just any anion that's combined with the H. When it dissociates, leaves H and A. So if we were to write this dissociation constant, Ka, that's going to be equal to the concentration of the products over the concentration of the reactants. So we have the concentration of H times the concentration of A over the concentration of HA. Okay, and the same for the Kb, except for it's backwards. Kb is the dissociation constant for a base. Now you think here that this A means acid. It doesn't. It means anion. So it's a negative ion or the anion. And when we write the dissociation constant for a base, it's better if we write water with it so that we can see how we get this acid and the hydroxide left over. But when we're writing the Kb for that, we don't include water because water is a liquid, and we don't include liquids or solids. So when we write the dissociation constant for a Kb, it's going to be the concentration of HA times the concentration of OH over the concentration of the anion here. And we know that Ka times Kb is equal to 1.0 times 10 to the negative 14th. That's the dissociation constant for water. Okay, so if we substitute this in for Ka and this in for Kb, let's see what we get. So we have the concentration of the hydrogen times the concentration of the base over HA. Okay, and this is times concentration of the acid times concentration of the hydroxide over the base for this one. Okay, now we're multiplying two fractions here, so we can cross cancel. So let me change colors here. So this A is going to cancel with this A, and this HA is going to cancel with this HA. So let's see what we have left over. If we write just what we have left over, we have the concentration of H times the concentration of OH is equal to Kw. Okay, and that's exactly what we saw in our last section. And Kw is equal to 1.0 times 10 to the negative 14th. So all of that in saying that if you are looking for the Ka, you can take 1.0 times 10 to the negative 14th and divide it by the Kb. And if you're looking for the Kb, which we will do in this section, we can take 1.0 times 10 to the negative 14th divided by the Ka. Okay, so make sure you have your Ka sheet handy and available so that we can use numbers from that. All right, and that's just a little concept review that we went over in our last section as well. All right, so let's look at non-buffers. So to appreciate the effectiveness of a buffer, we're going to calculate the pH of a non-buffered solution. And then as we go through this section, we'll come back and compare that to this non-buffer, the buffer solutions that we have. So let's just say we have a beaker of water. Okay, and in this we have 1 liter, and this is pure water. Okay, nothing in it but water. So what would be the pH of just pure water? Okay, we know the pH of just pure water is 7. All right, so let's compare that now to if we took this 1 liter of water. So let's take this beaker of water that we have, this 1 liter of water, and we're going to add to this 0.03646 grams of hydrochloric acid. And this is about the equivalent of a 30th of a Tylenol capsule. So if we took a Tylenol capsule and we ground it up, we divided it into 30 equal parts, we're just going to put one of those 30 parts down in here. That's really, really small. It's not a lot at all. So when we calculate grams into moles, this is going to be the equivalent of about 1,000th of a mole. So that's a very, very small amount. Okay. And we're going to put it into this container that contains 1 liter of water. Well, we need to get the molarity of the hydrogen ion concentration. Well, since this is hydrochloric acid, and remember, hydrochloric acid dissociates into hydrogen plus the spectator ion chloride. So if we have this many moles of hydrogen, since it's 1 to 1 to 1, we have that many moles of, since we have this many moles of hydrochloric acid, since it's 1 to 1 to 1, we have this many moles of hydrogen. Okay, and then to get molarity, which is what we need to calculate pH, we take moles divided by liters. All right, and since this is 1 liter, then we have 0.001 molarity. All right, and if we take the negative log of this, which is how we get pH, okay, then we're going to get a pH of 3. All right, so adding that just very small amount of hydrochloric acid, which is hydrogen ions, to this water now, unbuffered solution, it drops the pH to 3. Okay, and that's a lot. Each drop in pH represents a 10-fold drop. So 7, 6, 5, 4, 3. So if I start at 7 and I go down to 6, that's a 10-fold. Go down to 5, that's a 100-fold. Go down to 4, that's a 1,000-fold. And go down to 3, that's a 10,000 times more basic, 10,000-fold change. Okay, so this is 10,000 times a stronger acid than the pH 7. Okay, so that's quite a bit. That's a huge drop, as a matter of fact, from 7 down to 3. All right, so let's keep that in mind as we go through and discuss now buffered solutions. So in order to make a buffer solution is made from a weak acid or a base and its conjugate. Okay, so 1 liter of a 1 molar solution of acetic acid. What's the conjugate base of acetic acid? Okay, so let's think about it. We have CH3COOH, or remember, I told you another way to remember this is HC2H3O2. These are the exact same formulas, just written a different way. So what do acids do? Acids donate hydrogens. So if this loses a hydrogen, okay, and this is its acid, right? If this loses a hydrogen, then its conjugate base is going to be C2H3O2 minus. And this is the acetate polyatomic ion. Okay, acetate ion. So this is acetic acid. Acetic acid. Okay, so ic comes from ate. So if you have an acid that ends in ic, then its conjugate base is going to end in ate. Okay, acetic, acetate. Now, this needs to be bonded with, you just don't have acetate ions that you add. So this needs to be bonded with some kind of spectator ion. And so what they usually do is bond it with a group 1 spectator ion, because remember, group 1s are always soluble. So you'll see this is either a sodium acetate or a potassium acetate solution. Okay, so this is the acid, acetic acid, and its conjugate base is the acetate ion. All right, and this conjugate base acts as a hydrogen sponge, because look at the whole entire equation. Okay, so there's your acid, okay, and this dissociates into CH3COO plus H. Okay, now since this dissociates this way, but not very much, because it's a weak acid, not very much. It strongly wants to stay together because it's a weak acid. Okay, so if we add more acid, if we put hydrochloric acid in this and we add more of this is called Le Chatelier's principle. It's going to adjust its equilibrium to relieve that stress. And it doesn't like to stay apart. So to relieve that stress, it's going to go back together this way. So when we add more hydrogen, it's going to bond with this anion here, the acetate ion, and it's going to be driven towards this way together. So it soaks up these extra hydrogens that we're adding to it. So it's like a hydrogen sponge. And that's why buffers work. So it's a weak acid and its conjugate base, because it's a weak acid, it wants to stay together. And so any extra hydrogens that we add to this, these anions are going to soak it up and go back to the weak acid. All right. So for buffer formulas, remember the formula for Ka, which is Ka is equal to the products divided by the reactants. Okay, so we have H plus and then A over HA. Okay, now we're going to be rearranging this so that we solve for the hydrogen ion concentration, because the hydrogen ion concentration is what we use to get the pH. Okay, taking the negative log of the hydrogen concentration. So every single problem you're going to be working, you're going to use the same equation where we're going to solve for H. So let's rearrange this to solve for H. So what I want to do is multiply both sides by HA. So I'm going to write HE over here because we're multiplying both sides. Now what that does is it gets rid of the HA here on this side. Okay, and then we want to get rid of the A here to leave H by itself. We're going to divide both sides by A, like this. And so that gets rid of the A on this side. And so now we have H by itself. So the formula that we're going to use is the hydrogen ion concentration is equal to the Ka times the acid concentration over the base concentration. Every single time. So this is what you need to remember. Okay, so let's look at a problem. We're going to calculate the pH of a 1 liter of the 1 molar solution of acetic acid. Okay, so in order to do this, we need to have our ice chart. This is what we were doing in our last section. Okay, and that's going to dissociate into H and A. Okay, and so we're starting off with a 1 molar solution. This is going to go down by X. We have none of this and none of this. This is going to go up by X, and this is going to go up by X. So this is going to be 1 molar minus X, X, and X. Okay, and remember, this is equal to the Ka. Well, it tells us the Ka here is 1.8 times 10 to the negative fifth. And remember, when we're subtracting this very small amount that it's going to dissociate for a weak acid, this is so small that it's really not going to have a significant effect on this. So to make the math easier, we drop that off. So this is going to be X squared because these are the products, X times X over the reactants, which is 1 molarity. So this is just the square root of 1.8 times 10 to the negative fifth is equal to X. And so that's going to give us the concentration of our hydrogen. Then we can take the negative log of that and get the pH of this solution. So I'm grabbing my calculator. Okay, so the square root of 1.8 times 10 to the negative fifth is 4.243 times 10 to the negative third. Okay, I'm going to take the negative log of that, and it's going to give me a pH of 2.37. Okay, and that is a non-buffered solution of acetic acid. All right, so now to this, we're going to add a 0.001 molar hydrochloric acid. So we're adding more of this, more acid to this solution. We're going to see how that affects the pH. And this is of a non-buffered solution. Now, this is 1/1000th of a mole. I think it's the same as we added over here. Let's see. Yes, 1/1000th of a mole. Okay, and so, because it's in 1 liter. All right, so that is, here we have our concentration of 4.2. So we have 4.243 times 10 to the negative third moles here. And we're adding 1.0 times 10 to the negative 3 more. Okay, so let's add those together. We're going to get 5.243 times 10 to the negative third moles. Okay, and that's in 1 liter, so molarity. Now, if we take the negative log of that, 5.243 times 10 to the negative 3, we're going to get a pH of 2.28. All right, so it didn't change a whole lot. It only changed by a 0.1. Okay, but with that small amount, 1/1000th of a mole of hydrochloric acid, okay, and it does change it by that amount. And this is a non-buffered solution. So let's look at a buffered solution. Let's make a buffered solution. So calculate the pH of a 1/2 liter solution of a 0.5 molar formic acid. Okay, see here, formic acid, and a 0.7 molar sodium formate. Okay, so here's the acid right here. This is the acid, and this is the conjugate base, 8. All right, so let's look at this. Let's write our formula down here. We've identified our acid, we've identified our base, and that's going to be equal to Ka times the concentration of the acid over the concentration of the base. All right, so we know the Ka, it tells us here 1.8 times 10 to the negative fourth times our concentration of our acid. So it's going to be a 0.5 molar over 0.7 molar. Okay. And so it's a math problem here. And this is going to be equal to the concentration of the hydrogen. So let's go ahead and do that. 0.5 divided by 0.7 times 1. Okay, hold on. I hit a wrong button on my calculator. Okay, here we go again. 0.5 divided by 0.7, okay, times 1.8 times 10 to the negative fourth. Okay, that's going to give me the hydrogen ion concentration of 1.286 times 10 to the negative fourth. Okay, now I take the negative log of this, and I'm going to get a pH of 3.89. Okay, now remember, this is a buffer solution because we have a weak acid and its conjugate base. So this is going to soak up the hydrogens that we add. So let's just make it interesting. And we're going to add 10 milliliters of a 1.0 molar. And this is 10 times more acid than we added here. Okay, 10 times more acid to this buffer solution. All right. And so how many moles of this are we adding? Well, remember, to get moles, we do molarity times liters. So our molarity is 1, and our liters is 0.01, because this is milliliters. Remember, you have to change it to liters. Okay, so this is going to be a 0.01 moles. Okay, now let's convert this to moles, because here we have moles. So how many moles of formic acid do we have? Well, we have 0.5 times 0.5. So that's half of 0.5. So that's a 0.25, right? And then 0.5 of 0.7 is 0.35. So now we're in moles. Now we're adding an acid. So which one of these are acid? The acid's on top. So we're going to add 0.01 moles of acid here. And what's going to happen when we add this acid? It's going to combine with the base and remove that base back to the full conjugate. So I'm sorry, the full acid. So we're going to lose 0.01 moles of the base. Okay, because it's going to combine and go to the acid. So 0.25 plus a 0.1 is 0.26. Okay, and 0.35 minus is going to be 0.34. Okay, so we don't have this anymore. And we're going to multiply this by the Ka, okay, which is, where's the Ka? Right here. All right, so let's do that. So the first thing I want to do is my fraction, 0.26, just because it's easier, not because it's a rule that we have to do that. It's just easier to do the fraction first in your calculator and get an answer and then multiply it by the 1.8 times 10 to the negative 4. Okay, so I'm going to get a hydrogen ion concentration of 1.376 times 10 to the negative 4. Okay, now if I take the negative log of that, I have 3.86. Okay, so let's compare these pHs. 3.89, 3.86. We added 10 times more acid, 10 times more acid, and it only changed the pH of this 3/100ths of a point, where over here we added less acid. Oops, I went the wrong way. We added less acid and it changed the pH a full 0.1. Okay, so this is how a buffer solution acts. It soaks up acid and base. So it keeps the pH relatively the same. Now, if we were going to round this, right, 0.9, 0.9. So these would both be 3.9. But we took it out one more sig fig so that we could see that it's only 3/100ths of a point. Okay, so let's do another example. All right, so calculate the pH of a half of a liter solution of formic acid to a 0.7 molar sodium formate. Okay, so here's your acid and sodium formate 8. Here's the sodium. That is a spectator ion. So here's the acid and its conjugate base. We have a Ka here. So to get the hydrogen ion concentration, we are going to take the Ka, okay, and we're going to multiply it by the acid over the base ratio, acid to base ratio, and that's going to give us the hydrogen ion to get the pH. Okay, so 0.5 divided by 0.7 times 1.8 times 10 to the negative 4. Okay, and then take the negative log of this, and we're going to get 3.89. pH of 3.89. Is that the same? Oh, we're adding acid here. Okay, so here we're going to add the conjugate base. Okay. So it's the same problem, but on the previous problem we added acid, and on this problem we're going to add the base. Okay, so here is our spectator ion. Here's the base. We're adding 10 milliliters of the 1 molar base. Okay, so again, it's 0.01 moles. Okay, now looking back, we have the same 0.25 here, and we have the same 0.35. Now we're adding base. So we're not adding the acid, we're adding it down here, and we're getting rid of it up here. Okay, so this one is going to be a 0.24, and this bottom one's going to be a 0.36. Okay, and then again, we're at 1.8 times 10 to the negative 4th. All right, so let's see what this gets us when we add the base to it. Okay, 3.92. All right, and 3.89. So this is the same, 0.03, okay, but it's in the other direction. So it doesn't matter if we add acid or if we add base, you just have to make sure you remember which number in the ratio here that you take it away from, okay? And it's still going to change it the same amount, a very, very small amount. All right, so for our next example, it says calculate the pH of a 0.25 molar NH3 and a 0.4 molar NH4Cl. And we have a Kb here instead of a Ka. So it's the very exact same way, only this is a base, right? And it's conjugate acid. So what's our base? Our base is the NH3, okay? Our conjugate acid is the NH4. Remember, the chlorine is a spectator ion. So the acid, okay, is going to be the NH4 plus. All right. So plug it into the same formula. We have the concentration of the hydrogen is equal to the Ka times the acid concentration. Okay, so the acid concentration is 0.4 over the concentration 0.25 of the base, but we need the Ka and we have the Kb. So how do we do this? Well, remember, Kw is equal to the Ka times the Kb. Okay, and if we have the Kb and we want the Ka, then we just take the Kw divided by Kb, and that's going to give us the Ka. So 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. Okay. 1.0 negative 14 divided by 1.8, 10 negative 5th, 5.56 times 10 to the negative 10. Okay, so we substitute this in for this right here, and we get our answer. So 0.4 divided by 0.25 equals times 5.56 times 10 to the negative 10. And we get 8.896 times 10 to the negative 10. Now, if we take the negative log of this number, it's going to give us a pH. And we get a pH of 9.05. So you see, it doesn't matter if you have an acid or if you have a base, you do the exact same formula. This just required one more step here to get the Ka, because since this is a base, the Kb was given to us. Okay, but it's exactly the same formula. All right, so you may be asked to solve for something besides the pH. Like, say, for example, using acetic acid and sodium acetate solutions, which is a buffer solution, make a buffer with the pH of 5.0. Okay, so we need to look at our formula. So the concentration of the hydrogen ion is equal to Ka times the acid over the base. Okay, so this right here is what we're looking for. Okay, we need to know how much acetic acid and how much acetate to put in the solution to make this. So we know the pH here is 5. And how do we get the hydrogen ion concentration from the pH of 5? Well, remember, it's 10 to the negative pH. So the hydrogen ion concentration is going to be 1 times 10 to the negative 5th. Okay, we can look up the Ka for acetic acid on our Ka chart. And when we do that, we're going to see it's 1.8 times 10 to the negative 5th. And let's just call this X. This right here, HA over A. Let's just call that X. All right, so now to solve for this right here, we just divide both sides by 1.8 times 10 to the negative 5th. And that's going to give us X, which is our ratio here. Okay, so 1 times 10 to the negative 5th divided by 1.8 times 10 to the negative 5th. And we get a ratio of 0.556. Okay, so what's the best way to make this a fraction? Because this is a fraction, put it over 1. So what does this tell us? This tells us that we need, and let's just assume we're making 1 liter because it doesn't tell us. So that makes it super duper easy. We need 0.556 moles of acetic acid. And we need 1 mole of, I don't know, let's call it sodium acetate. Okay. Now, if the problem tells us we need more, like it says, we have, we want to make this a 2 molar solution instead of a 1 molar solution here, then all we have to do is just double this top number. Okay. So simple. All right, and that's it for buffers. So make sure you slap that like button right across the face. Make sure you subscribe and you poke that notification bell so you know when I put up new videos.